Hi everyone, and thank you for joining us today. My name is Morad Nakhleh, Head Commercial Biomarker Strategist at Allstone Medical. And today, with my colleague Jason Kinchen, Lead Biomarker Discovery Scientist, we will introduce the Breath Biopsy OMNI assay for comprehensive and reliable detection of volatile organic compounds as biomarkers in breath. We will also share with you examples of applications of OMNI and data from interesting case studies. Our mission at Allstone Medical is to save 100,000 lives and 1.5 billion in healthcare costs. And this is through the provision of clinically valuable breath-based tests that could be integrated in clinical practice for early detection of diseases and precision medicine. However, the first step in this journey still heavily relies on our ability to discover and validate clinically valuable breath biomarkers. Now, in the last 20 years, the global breath research community has focused a lot on trying to answer this specific question. Do breath biomarkers exist? Could volatile organic compounds represent biological signal and be objectively measured as biomarker of disease? Let's take a look into some key facts related to this question. The first, we know that exhaled breath is a very rich biological matrix. It contains organic, inorganic, volatile, and non-volatile, endogenous, but also exogenous compounds that not only reflect on the status of the lung fluids, but also mirrors the chemistry of the blood. Breath biomarkers already exist. CO2, hydrogen, methane, nitric oxide, and others are already in clinical practice. We know about hundreds of VOCs and their links to biological and metabolic pathways, such as aldehydes in oxidative stress and ketones in glucose metabolism. We've seen dozens of clinical trials that ended up with promising results and potential biomarkers in a wide range of diseases. However, there is still massive lack of success when it comes to replication or validation of those results. And that, of course, impacts the translation to clinical use, where we see it very limited to almost absent in terms of VOCs as biomarkers of diseases. Now, that could indicate a limited potential of VOCs to be biomarkers of diseases. However, that also could indicate challenges in the field that we need to tackle first in order to improve the chances of translational aspects of VOCs being biomarkers of diseases. Now, it's no secret that the field has been associated with historic challenges that negatively impact the reproducibility and reliability of results. In 2007, a review written by Anton Amman's group stated, analysis of exhaled air is not currently being used as much as it could be because of difficulties in the methodology, sampling and analysis, and lack of basis for data interpretation. There are no normalized systems for sampling, thus making it difficult to interpret the results. However, and very unfortunately, even today, when we look into the literature, we still see the same messages about the lack of standardization again and again. In 2019, this is likely due to the lack of standardized equipment for breath sampling, standardized collection methodologies, as well as appropriate controls for potential VOC contaminants. 2021, just a few weeks ago, challenges such as standardization still need to be addressed in order to reach clinical validation. And therefore, the OMNI assay was developed as a fit-for-purpose end-to-end breath sampling and analysis platform with a focus on tackling those historic challenges. So the first is to provide a high reliability and reproducibility of sampling, because otherwise we introduce a huge variability that could mask any biological signal. To provide a high analytical stability and consistency, to eliminate the chances of bias and drifts over time that could impact the reliability of output of large clinical trials, and of course, the elimination of contaminations and false discovery compounds that might end up in breath sample, but their main source was never exhaled breath. Those might end up in our statistical analysis and showing us what is known as voodoo effects and faces in the clouds. We do that by using the state-of-the-art sampling and analysis technologies. On the breath collection side, we use the receiver breath sampler for reliable, reproducible sampling, with Casper for provision of cleaned inhaled air during the sampling session, minimizing the contaminations, and those are controlled by the breath biopsy collect software. On the analysis side, we use TDGC high resolution accurate mass Orbitrap system to maximize the sensitivity to get the broader linear dynamic range and reliable identification of volatile organic compounds on breath. Now, we took the philosophy of the OMNI assay and translated that into two key requirements. The first is we need to provide a platform for global detection of exhaled VOCs representing biological signals, which means we need to maximize the range of detectable VOCs by the platform, but we also need to ensure that those VOCs are on breath. In other words, their main source is actually the human breath. The second key requirement is we need to have the ability to quantify changes happening in that biological signal, because this is what biomarker is. And that means we need to minimize the process variability to expose that biological signal. We need to minimize the error introduced pre-analytically and analytically to see the true biological signal. Now, we know that when we analyze breath samples, we see hundreds, if not thousands, of volatile chemicals in our chromatograms and in the final output. However, not all of those have the potential of being biomarkers. Compounds that are not coming from breath cannot represent biological signal and therefore cannot be biomarkers. Now, when we quantify a volatile organic compound in breath, what we are measuring is the total quantities of that VOC coming from all different sources and ending up in that sample. And those sources could also include ambient contaminants, what we inhale, traces on the tubes, contamination in collection bags or the hardware, or even during handling, VOCs could leak into those samples and produce false peaks. So in some cases, all we're looking at are basically contaminants, like in the right hand example. It's only the gray or the undesired sources of VOC ending up as a peak or a compound on the chromatogram. In other cases, there is a breath a signal with a wide range of signal to backgrounds. As the one in the middle, it's a poor signal to background, which means the signal is dominated by the background, while the one on the left has a massive signal to background, which means it's actually on breath VOC. And the distinction between those is very, very important. And I'll show you why in few examples. In this experiment, we collected 35 breath samples from volunteers as well as representative system blanks. Those blanks are meant to capture all of the undesired sources of VOCs that might end up in breath samples. Now, you could easily see that for isoprene, for example, the vast majority, if not all of the signal is actually coming from breath, since it is absent in the blanks. Thus, it is on breath VOC. And therefore, changes in exhaled breath concentrations of isoprene are expected to be well quantified by our platform. Now, to test this, we collected double the collection volume, and that translated into a good and obvious response by the system, as you could see on the right side. However, it wasn't the case for 1-butanol from the same experiment. As you can see, there is no much difference between the concentration of breath and the blanks, and thus we cannot claim that this compound is actually coming from breath or could represent a biological signal. That also translates into a very poor system response, When we collected double the collection volume, we barely saw 5 to 10% change in the concentration. And this is what is expected by VOCs dominated by the background contamination until we improve their signal to background ratio. By the way, there was statistical significance when we compared the breath and the blank concentrations of one butanol, which is a very common method used in the literature nowadays to provide some sort of evidence that the compounds actually coming from breath. However, I think that this data and these results are evidence that this approach is not robust enough to make that determination. Therefore, we started by defining on-breath VOCs as the VOCs that their concentrations across different samples are at least 3 standard deviations above the mean representative background. We also defined a standardized way for testing and reporting the results, which we call the BOP study or breath or blank, in which we take, as I showed you before, repeated sample from a single volunteer, or we sample a small population. We also collect equal number of representative background blanks. And for each VOC, we determine if it's on breath or not based on this formula. And for every BOP study, we report on the same metrics, the number of on-breath VOCs detected across samples and their variability. We use those specific metrics all along the development and testing of the OMNI assay, allowing us to make decisions regarding the configurations and settings of the platform. And the goal was all along the way to choose the settings that would increase the number of on-breath VOCs that we repeatedly detect across samples and minimizing the variability of those compounds. Now, I would like to discuss the reduction of contaminations, mainly from ambient sources and their impact on false discovery. Now, to do so, we performed a study in which we collected blanks and breath samples under normal conditions and then under extreme conditions of contamination. That contamination was controlled that we actually induced. And since we knew the components of that contamination, we were able to monitor those in different samples and learn from their behavior. Now, eucalyptol was one of those compounds, and we started the experiment by obtaining an ambient sample and a blank from Casper, showing that basically eucalyptol was absent. While on a breath sample, we see on-breath eucalyptol, which we'll refer to as the biological signal of interest. Now, when we introduced the contamination, we could see the positive control. The ambient concentration of eucalyptol is extremely high, and the following breath samples that were obtained still showed much similar concentration to the original biological signal when compared to the ambient concentration. However, to make sure we're not seeing some coincidental results, we took additional breath samples, however, this time allowing some leak into the system. It could be done by making a hole in the mask or releasing the mask for a few seconds. And we immediately saw that the breath concentration now, what we're measuring, reflects the concentration and variability of the ambient air in that room and not the biological signal itself. And this is how we learned that by using a receiver with Casper, we are able to eliminate high concentrations in the ambient. Our platform is basically resilient against ambient contamination. And as you can see here, false discovery, since the signal does not represent the biological signal anymore. Still within the sampling aspects, one question we had to answer is which part of the exhaled breath we are more interested in sampling. And we had two options, a whole breath, or also known in the literature as mixed, compared to the lower fraction of exhaled breath, which is known as the alveolar breath. Now, the main difference between the two is that the whole breath contains the dead space volume. And our concern was that due to differences in the anatomy and physiology of different people, including the dead space, might end up with variable dilution of the samples. So to test that, just like I showed you before, we performed a BOP study. We took 10 breath samples from a volunteer, and we used this very cool feature of receiver, allowing to capture different fractions of exhaled breath on different tubes. So one side collected the lower fraction, while the other side collected all the time to capture the whole exhaled breath from the very same exact breathing cycles. When we analyzed the data, just like I showed you, we used the formula of 3 standard deviation above the mean background to determine which compounds are on breath. We discovered that with the lower fraction, we get 36% more on breath VOCs in our final output, as well as 55% lower in the variability in those samples. And that showed us that collection of the alveolar fraction of exhaled breath allows us better reproducibility, consistency, and lower variability. And therefore, it was our choice to continue using that fraction in the OMNI assay. We also validated those in a targeted analysis with 40 known on-breath compounds, and we saw a very similar result. Now, just worth mentioning that we need to keep in mind that sampling could be application dependent. So if we're looking into an oral disease, for example, we would be interested in collection of the dead space or VOCs that come from the oral cavity. And in that case, we could just change through the software of receiver to collect the whole breath or even only the upper part of the exhaled breath fraction. Still within a sampling, one of the questions was how do we optimize our sampling volume to maximize our performance metrics, the number of on-breath VOCs and their variability, as well as the analytical split. Now, as I said, for VOC to be considered on breath, it needs to be above the background. But first, it needs to be above the limit of detection. We need to see it first. And here's just a couple of examples on when we started testing for different volumes and splits to optimize the performance. There were 2 main patterns of behavior that we saw. On the right side, you could see compound that we saw for the first time with the optimized settings. It wasn't even detected before. Now we can see it in the breath sample. It's absent from the background, and therefore it's on breath VOC. On the left side, you could see compound that we saw previously with a lower volume, but the signal to background was poor. You could see that the concentrations overlap between the breath and the blank. And when optimizing for the volume and the split, we got a much better signal to background. And now it qualifies as on-breath compound that we could measure with the OMNI assay. And this is the type of development, and again, testing against the standardized metrics report and have data-driven decision-making by trying to improve the number of on-breath compounds and reducing their variability. Now, the other challenge that we discussed was regarding the analytical method and instrument variability and stability. And we tackled this in OMNI assay by introducing a very thorough quality control means. We introduced internal standards that are injected to every sample analyzed in the system. We have a ratio of 2 quality control samples for each analyzed breath sample in our sequences. We run 52 calibration curves every sequence for relevant VOCs that allows our application chemists to assess the sensitivity, limit of detection, linearity, and behavior of the instruments along the analysis sequences of clinical trials. And this is how it looks. So as I said, every sample is injected with 8 internal standards. We perform the sequence analysis, and by the end of the sequence, we have the output, the recovery, and variability of those internal standards. On the left side, you could see when the system is well behaving, a very low variability, about 5% RSD, within the limits of acceptance criteria. We're happy with it. We continue and run the following sequence. However, on the right side, we could see indications for when the system suffers from any problem that reflects on the variability and behavior of the internal standards. Now, we know that this would also reflect on the breath samples themselves. In that case, we stop, we test, we correct, and only when we meet the acceptance criteria, we continue to the following sequence. What that allows us is to keep the analytical variability as low as possible, spot problems in their early stages to correct. That improves our sample yield, because samples that fails the acceptance criteria typically are excluded from the statistical analysis, and therefore by spotting those problems early, we save as many samples as we could, and in general that improves the quality and the confidence that we see in the results and findings of those studies. The aspect that I would like to share with you is regarding the data processing development for the OMNI assay. Now, this is a key step in which allows us to translate the data into information that we could use for statistical analysis, interpretation, and identification of potential biomarkers. And regardless of how well the platform is performing, errors in this step would lead to problems like false discovery, loss of potential biomarkers, low quality, irreplicable data, and basically faces in the clouds. Our chemoinformaticians team optimized this process and developed a tailor-made data processing for the OMNI assay, while still focusing on the same capability metrics that we discussed previously: the number of on-breath volatile organic compounds, their variability, as well as quality metrics specifically for this process. And what we see following the optimization of the parameters of the settings of those algorithms, that from the same set of data, we can now see more than double the number of on-breath VOCs that we detect across different samples. Now, those compounds did not just magically appear, but this is as a consequence of better sensitivity, selectivity, more accurate integration among or across different chromatograms, as well as we saw improvement in the quality. So the number of missing VOCs that the algorithm missed before is now reduced by 30%. Our ability to detect compounds that we know they are there is almost 98%, and we reduced the amount of manual intervention that required to correct errors in the data by over 20%. Now, if we zoom out and look into what this process provides, you can see clearly improvement in the biomarker discovery capability, as well as a higher quality and reliability of the data that gives us much more confidence when we discover potential biomarkers. So how does the data look from the OMNI assay, and what are our current capabilities? So to test this, just like I explained before about the BOP study, we did something similar here, a bit more challenging than typically, in which we took 57 exhaled breath samples from 4 different volunteers at 4 different days, equal number of representative system blanks for every volatile organic compound, started by looking into the blanks, understanding what the background is, and based on the formula, only ones that scored at least 3 standard deviations above that blank were considered on breath and being presented in this slide. So the median number of peaks or VOCs that we could detect per sample was 1,454. And from those, 517 in median were considered on breath based on that description in every sample. Now, if you look into this plot, it describes the repeatability of those volatile organic compounds across different samples. Now, for example, 266 volatile organic compounds were found on breath in at least 70% of the population here, which is the 57 samples, while 392 volatile organic compounds were found on breath in at least 50% of the samples, while 647 were found on breath in 25% of the samples, representative of a single volunteer in this case. In terms of top-level investigation of the data quality, a PCA for all of the analyzed samples shows that we easily distinguish between the different types of samples based on their content. We saw two clusters, one for breath in blue and one in orange for the system blanks, as well as a very interesting third cluster indicating the similarity between samples directly obtained from Casper and clean unused tubes, indicating how clean Casper air is, so it's not contributing more content to those tubes. To assess trends in the data that could be caused by analytical platform, every sample in the same PCA was now colored by the analytical sequence number, and we had over 20 sequences in this case. And you can see that there is a good distribution without any specific trends that could impact or explain the data and the output that we are seeing. In terms of the data variability, we looked into the median relative standard deviation of 392 on-breath volatile organic compounds that we detected in this study. And while the intra-subject variability ranged between 25 to 36% in each of the volunteers, the combined data of all 4 volunteers showed a median relative standard deviation of 49%. Now that includes the biological variability, the 4 different volunteers, pre-analytical variability as the sampling was spread over a period of 1 week, and of course the analytical variability as the samples were analyzed on the OMNI platform over a period of 1 month. The table on the right indicates the variabilities of the internal standards that were recorded along the study, and as you can see, ranging between 3 and 13%. At the end, what makes the OMNI assay different? So as I showed you, we have optimized the sampling procedure, increasing the signal to background ratio to maximize the number of on-breath VOCs that we could measure. We detect and analyze a very wide range of exhaled volatile organic compounds. We have provided and tested our system to be resilient against environmental ambient contaminants, minimizing false discovery rates and decreasing the process variability. We maximize the number of on-breath VOCs that we could detect. As you have seen, we have the capability of reliable detection of up to 500 on-breath compounds per study, and we introduced over 50 calibration standards in every analytical sequence that allows us to monitor the system. We have minimized the end-to-end process variability, so our quantitation ability is much better, allowing us to identify changes in biological signals. And we have developed online analytical quality control measures with the internal standards, with the over 50 calcars that we run, that gives us higher confidence in the findings and reliability of the results. And at the end, by this development and using the high accurate mass Orbitrap, we have now an easy route to identification of novel compounds of interest once we spot a potential or candidate biomarker. Now, OMNI has become Ostone's signature platform, used both internally and offered to our customers and collaborators for answering their most critical questions in breath research and biomarker discovery studies, providing high quality and robust analysis for their clinical trials. The OMNI assay has been designed to provide the broadest possible measurement of on-breath VOCs with minimal process variability, making it ideal for biomarker discovery studies and volatile organic compounds investigation trials. Now, before handing over to Jason, I would like to share with you our vision of the future of breath analysis and the OMNI assay. We have recently kicked off the first human volatilome sequencing project, in which we are going to identify all of the detectable on-breath VOCs. And based on this, we will develop a bioanalytical method for targeted global analysis for all of those on-breath VOCs. Now that would allow us to measure those VOCs in every future project and pool the data into a huge database in which will include the absolute concentrations measured in those thousands of patients, comprehensive demographic and clinical data, and would allow us, of course, to start better understanding the sources and the related biological pathways of each of those volatile organic compounds. I will now hand over to my colleague Jason, who will talk about applications of OMNI and share interesting data from case studies.
Hello, my name is Jason Kinchen, and I'm going to discuss applications for breath biopsy. As a high-level overview, I'll first walk through a comparative case study describing some of the first results we've achieved with our OMNI analysis, conducted in collaboration with investigators at the Mayo Clinic. Next, I'll walk through a case study describing applications of breath biopsy to hepatic disease, containing both internal work and a study conducted in collaboration with Cleveland Clinic. Together, these pieces of work describe the potential for breath biopsy for identifying previously unrecognized roles for volatile metabolites as biomarkers reporting on health and disease. Exercise is associated with many health benefits, including increased overall cardiovascular health and longer lifespan. Prolonged exercise in extreme environments, however, such as the high-altitude marathon week study here, can induce spontaneous lung injury with phenotypes similar to disease, such as pulmonary edema. Here, we have a comparative study undertaken in partnership with Dr. Bruce Johnson from the Mayo Clinic. This project is somewhat unique, as it allows us to interrogate the impact that a methods revision can have on detection of compounds in breath. Here we assess a population of ultramarathon runners, sampled pre and post-run, either on our old platform or our new OMNI method. As can be seen in the volcano plots to the right, the OMNI method allows the identification of a substantially increased number of compounds. In the previous method, a large increase in one compound, tentatively identified as acetate, saturated the detector, leading to difficulties in data analysis. This was not the case in the OMNI method. The broader dynamic range of the Orbitrap allowed quantitation of this feature and moderated impact on neighboring peaks. In conclusion, OMNI led to a number of performance improvements in this context, which then enabled biomarker discovery. When considering applications, respiratory diseases are high on the list due to the proximity of the breath matrix sampled to the lung. However, breath is relevant also to non-respiratory disease. The lung alveolar space is designed to enable the efficient exchange of oxygen for carbon dioxide. As a corollary, volatile compounds are also exchanged here from the blood, meaning VOCs produced by distal organ systems are available for analysis in breath, enabling biomarker discovery here. In the next set of slides, we'll consider hepatic disease as one application for breath. Liver disease has a high prevalence in the West. Risk factors for disease development include obesity, metabolic disease, as well as exposures, such as chronic alcohol use. Incidence of these risks themselves are increasing, meaning that incidence of liver disease will also increase in the coming years and represent a high cost and burden to the health industry. At the moment, diagnosis is typically late in the course of hepatic disease, at decompensation, with few treatments available to delay progression and eventual needs for liver transplant. A diagnostic panel for early detection and/or estimating risk of progression would have a large impact both in the clinic as well as the pharmaceutical research space. Today, I'll present work in the academic literature as well as conducted at Owlstone, identifying breath biomarkers for hepatic disease. Perhaps the most extensively assessed application for breath in the literature involves the use of limonene as a biomarker in breath of hepatic disease. As one example, a study by Fernandez del Rio et al. Assessed a small pilot cohort of subjects prior to and following liver transplantation. Elevated levels of the dietary compound limonene were found on breath, which then returned to baseline levels following liver transplantation, suggesting this compound as a robust marker for disease. Why is limonene, a dietary compound, elevated in breath from subjects with hepatic disease? Well, blood from the intestine is filtered by the liver prior to entering the systemic circulation. In the liver, compounds like limonene, a plant-derived terpene, are metabolized by the cytochrome P450 system, a family of enzymes with wide-ranging roles in catabolic and anabolic reactions. Relevant to this discussion, these enzymes play a primary role in detoxification of dietary compounds, including drugs. Two CYP2C family members, CYP2C9 and CYP2C19, specifically metabolize limonene in addition to a number of other compounds. Expression of these enzymes is downregulated in cirrhosis, leading to the increases in limonene levels observed on breath in the previous study. Using Owlstone's breath biopsy, we approached hepatic disease with an aim to replicate these findings, as well as to extend them by identifying additional biomarker candidates. First, we used a pilot study comprised of 40 control and 44 cirrhotic subjects. Untargeted analysis and biomarker discovery is still in process for this study. However, we were able to replicate findings with limonene and cirrhotics, as well as showing correlations between biomarkers of liver function and damage with this compound, as well as disease severity, as represented by child Pew class. Additionally, we also show that this molecule performs quite well in a discriminant model. We have also profiled a separate cohort of subjects with hepatic disease in collaboration with Dr. Daniel Rotroff at Cleveland Clinic. Here, we assessed a small pilot study of subjects with a goal of opening the aperture and identifying additional candidate biomarkers associated with liver disease, here represented by subjects with cirrhosis or hepatocellular carcinoma, using untargeted discovery methods. Limonene belongs to a larger class of molecules termed terpenes. In this project, we found strong associations of compounds tentatively placed in this class with hepatic disease, here labeled in orange in the volcano plot to the left. As one example, molecular feature, or MF78, is shown in the box plot to the right of the volcano plot to give an idea of sample distribution. These compounds also correlated well with disease severity, as represented by MELD score. We've begun a deeper assessment of findings in this project. For example, several VOCs tentatively identified as ketones also associated with disease, which may reflect changes in fatty acid oxidation known to occur with hepatic disease. As we continue to evaluate these results, we expect to identify additional biomarker classes of interest. Breath volatile analysis has many methodological and technical challenges, including the interpretation of findings. If we consider ketones, for example, a short ketone like acetone has a long history of association with fatty acid oxidation, particularly in the context of diabetes. However, an expert understanding of biochemistry is needed to place related volatile biomarkers into a metabolic context and assemble a metabolic pathway like the one shown here. Unlike the more developed field of plasma metabolomics, analysis of breath is just beginning to place identified compounds within an overall metabolic framework, associating discovered VOCs with underlying metabolic pathways. In terms of paths forward, this is one of the most time-consuming and most interesting steps in the process. That is, translating observed changes in biochemicals into biological context and providing informed choice to support downstream validation efforts. To conclude this talk, as we've seen in the previous slides, breath biopsy can be used to identify candidate biomarkers describing hepatic disease as well as severity of disease. There are a number of potential applications here, from clinical use to diagnose existing disease or early disease, as well as potential to quickly and non-invasively identify candidates for pharmaceutical therapies. As we come to the end of our presentation, I'd like to highlight several of the benefits of our non-invasive breath biopsy platform for enabling biomarker discovery. First, we provide a standardized breath collection methodology and couple this to our new OMNI method for high-quality data analysis. For many diseases, the resulting VOC dataset represents a previously unsurveyed data stream, which then contains the potential for unique orthogonal readouts. Owlstone provides comprehensive resources to design effective studies, collect and analyze VOCs, and work together to interpret the resulting data to select appropriate biomarkers for the question at hand. At this point, I'd like to thank everyone for attending this presentation, and I'm happy to answer any questions that you might have. Thank you.
Thank you to Morad and Jason for those presentations. We're now going to take part in the Q&A section of the webinar. So we've already got a few questions that are popping up in the Q&A function. If you've got any more, then please do submit them through that button, and then we'll get started. So we've got Jason, Jeff, and Julia joining us, all the J's. So I'll try and make sure that I mention who I'm asking this question to. But if one of you has anything else that you want to say related to any questions, then do just let me know. So the first question we've got here from Jonathan is for you, Julia, I think. How did you go about selecting the standard compounds and how representative are they of the VOCs you can detect on breath?
Yeah, okay, thanks, Laura. So I guess there's two types of standardized compounds. So we have 52 compounds that we run in our Kel curves at the beginning of the OMNI sequence. So those 52 compounds were chosen because they're commonly found in breath samples. Some of those are on breath, so 3 standard deviations above background, while others are not. So it's useful to both track the behavior of on-breath compounds as well as your contaminants when you're analyzing the breath samples. So that's how those 52 compounds were chosen. But we also have our internal standards, which are the compounds, they're deuterated compounds that are injected into the breath samples themselves. And they're basically chosen to be sort of distributed along the chromatogram by retention time to serve as a good proxy for the behavior of our on-breath compounds.
Already answered one from Sean, so I'll just go over that. So he asked, did you detect acetone and formaldehyde? Did you spike IS into breath samples, and what was the recovery percentage of these? So you've said that we do detect the acetone on the breath, and we do spike the IS into the breath samples, and the recovery is 100% plus or minus 15%. Is there anything else that you want to say there, Julia?
No, I think that covers it.
That one covers that one. Thank you. So we're getting quite a few coming in now. Jason, there's one here for you from Anil. And why were patients with fibrosis not included in the limiting breath test study in collaboration with the Cleveland Clinic?
Okay, so we did include subjects with pretty advanced disease in that study, and really it can be thought of as a bookend analysis, because these are in many ways people who are waiting for liver transplant, so they have fairly advanced disease.
Jeff, I've got one here for you. It's asking, could you describe the sampling system?
Yeah, so the sampling system, there's the receiver, which is the actual device for capturing the breath sample, and then the Casper, which is the clean air supply, which is about the size of a small printer, and a laptop to run the software. And so those that system is placed within a clinical site. We provide online training to use it. It's straightforward. It takes about 90 minutes, and then samples would be collected there. The samples are collected onto thermal desorption tubes, which require high heat to remove them from the tube. So a nice benefit of this is that samples can be sent using ambient conditions. They don't need to be stored and shipped. And then as the samples are collected, they would get shipped back to Alstone for analysis.
Okay, great. Thanks, Jeff. Julia, I've got one for you. This is from Alexander. He's asking whether there are any standard compounds affected by circadian rhythm, and is daytime standardization necessary when considering breath sampling in clinical studies?
That might be one for me.
Okay, Jason's going to answer it, but you were on mute, Julia. Thanks, Jason.
Yeah, so there are a fair number of compounds in metabolism that are affected by circadian rhythm. So just taking a parallel from hepatic metabolism, so compounds like the ketones that we saw in the presentation would be an example of a class of compounds that should be affected by circadian rhythms. There you have the metabolic processes like fatty acid oxidation, which oscillate based on substrate availability. So when you take in dietary compounds, you take in glucose, and that shifts the metabolic focus away from fatty acid oxidation towards oxidation of easier, more available substrates like that glucose. That really defines and underlies the shifts that you see in circadian metabolism. So those kind of drivers will also be reflected in breath data sets. In terms of standardizing collection to take advantage of that, I think the most important thing there is to sample consistently. Don't sample your groups where the controls are sampled in the morning and your cases are sampled in the afternoon. Randomize them across that process so that the circadian effects then average out within your collection.
Thanks, Jason. There's another one here for you, Jeff. It's asking how long it takes to process a sample.
Well, how long does it take on the collection side, it's about 10 to 15 minutes. In terms of the processing on our end, once we get the sample, we run all the samples together. So we would wait till sample collection is completed to run all of the samples. And then it's probably going to be 4 to 5 months before we're able to deliver the data on that. I don't know if I'm the best person to answer that question, if anyone wants to add something.
Does anyone want to add anything there? Nope. Okay, we can move on. So I see there's another question that's already been answered. So somebody's asked about internal standards added to samples collected on the TD tubes, and can you provide the separation method used for your analysis? So Julia's gone back there with internal standards injected onto the sorbent tubes after dry purge and before analysis. Separation is done by the GC column, chosen especially to maximize the number of on-breath compounds. Is there anything else that we want to say with that one?
No, I don't think so. Sorry, I was struggling to find my unmute with that previous one.
It's okay. So we've got another one here for you, Julia, on can Bob studies be used with other breath analysis methodologies?
Yeah, so the idea of comparing signal to background is a fairly sort of standard way of doing any kind of system development. So what we're doing here, identifying on-breath compounds that are above the LOD or 3 standard deviations above the background, is something that could be applied to different analysis methodologies for sure. It's not something that's specific to our Orbitrap or even our breath sampling. So yes, the answer is that sort of the way we identify compounds as on breath the way we count them, for sure, can be sort of applied across different methodologies.
Thank you. There's one here from Jacob. Can you identify where noise in a specific sample set is coming from, e.g. differences in drug, diet, etc.? So Jason, do you want to take that one?
Oh, I'd love to, because I think that's one of my favorite topics, because playing detective in the data sets is really quite interesting. There, it really depends on what type of metadata you have available to you. So when we run projects, we try and bracket as much of the clinical metadata as we can, so we can look for those effects in the data and then compensate for them in our statistical analyses. But really, it's very dependent on having access to descriptive variables where we can identify what those factors are that are driving differences.
Great, thank you. We've got one here. Is there any evidence so far of a VOC signature in a discovery cohort then validated into that's then validated into a validated cohort in any disease using the OMNI platform? Julia, do you want to take that one?
Sorry, Laura, can you repeat that question?
Yeah, sure. This question is from Sylvia. She says, first of all, she does say great talks and very convincing approach. That's really nice to hear. Thanks, Sylvia. Is there any evidence so far on the VOC signature in a discovery cohort that's then validated into a validation cohort in any disease using the OMNI platform?
Yeah, thank you. Great question. I'll start by saying the OMNI platform is fairly new. It's our sort of latest development. So it's something that we're using at the moment on some really exciting studies. It's not something that we have the opportunity yet to sort of take observations from an initial study and then take those through to validation using that platform, but it's certainly something that we hope and intend to do with our new technology going forward.
I think we've got a liver example with that that we could go through. Jason, do you want to talk us through that?
That might be referring to the two case studies that we recently presented. Just the first one, our internal study was done on not the OMNI method, but what could be considered a related method using the ThermoQ exactive system. So there we again saw this replication of the limonene findings, which could be viewed as a validation of some of those early results.
Thank you. So the next one is, how comprehensive is the ability to use breath to monitor the whole body? Jason, do you want to take that one?
Yeah. So because you have a continuous flow of blood through the body and availability at the lungs for air exchange, you can readily monitor different effects that are occurring at distal areas of the body at the lung.
Excellent. And we've got one here that's just coming from Sarah. How would you be able to elaborate more on discriminating diseases? Several diseases are associated with increased oxidative stress and have formation of common oxidative stress biomarkers.
Yeah, that's a difficult one. So there you have to really look into substrate availability. So a different spectrum of reactive oxygens or different spectrum of biochemicals is formed after reaction with different reactive oxygen species, depending on what the availability is at the head of that process. So depending on, for example, the availability of different lipid species, you can generate different oxidized outputs at the back end, and it's changes within that spectrum. So an increase of nonanal, for example, in one disease might not show up in another disease. So you can still have the same biological process undergoing, but the output there is different in terms of the specific composition of biochemicals that are produced.
We've got one here from Jim. Have you ever thought about using breath analysis for environmental exposure? I'm not sure if anyone wants to take this one. I'm going to pick on someone if not. Julia, do you want to take this one?
Yeah, I can do, yeah. So for sure, it's something that's interesting for us. I think from a technical perspective, there's no reason we couldn't use the OMNI platform, and certainly the learnings that we've taken from the development to look at environmental exposure. I think Jason's better placed to sort of comment on the biology behind it. There's no reason, especially with the fractionation capability we have, sort of being able to narrow in on either the upper fraction or the lower fraction of the lungs, depending on what exactly it is that you're looking for. But we have that flexibility in our technology to be able to narrow in on different questions.
Great, thank you. Is there anything you want to say with that one, Jason, in terms of the biology?
I think I agree with Julia. It'd be really interesting to see what the impact of some of these volatile air contaminants might be on biological processes that are ongoing in the lung, as well as systemically within the body.
Great, thank you. I think we've got time just for one more. So we've got one here from Mitchell. Do you rely on HRAM for TICs, or are you using other processes? Julia, do you want to take that one?
Yeah, I can take that one. So we have our own in-house HRAM library that we use for the identification of compounds. So when we compare our VOCs back to our HRAM library, we have a high confidence in the identity of those compounds. We can also use the NIST library, though. We did quite a lot of work to characterize our capability of using the NIST library with our Orbitrap platform. And actually, we get a really good sort of hit rate, accurate match rate to the NIST library as well. So we use both of those techniques to provide compound identification with our OMNI platform.
Thank you. Just come in from Alexander. Is there a list of VOCs in human breath available anywhere?
Yes, but it's kind of very out of date at this point. Yeah, it would be really great to have that resource. In some ways, areas like HMDB do annotate some volatile compounds, but it's very incomplete.
Julia, was there something you were going to say there as well? Yeah, I was sort of going to continue from what Jason said there. So it's something that we're looking at, obviously, throughout the development of this technology. We've been learning more and more about what's on breath in different populations. So it's something that we're sort of looking to do at Aylstone, is we're sort of creating that knowledge ourselves in-house.
Great. Well, thank you very much, everyone, for answering these questions. There's a couple that we haven't quite had time to get to, so we will either type the answers to you, or we'll try and get back to you tomorrow with those. Thank you very much for joining us this evening.